Okay, this is the ACS Organic Chemistry Study Guide, second edition, chapter 1, and we're going to start with practice question 1. Chapter 1, which deals with structure, shape, and stability. Okay, so question number 1, let's get started. It says, what is the equivalent bond line formula for the molecule shown here? So if we start out with this methine, remember a CH is called a methine. A CH2 is called a methylene. And of course, a CH3 is a methyl. So if we start with that methine, that's CH. So I'll just put a red dot over here and just kind of work on the side. Then we go off to the left to this methylene. So we have a methylene over here. Then we have the alcohol attached to that. We have this methyl group. So this methyl group here is attached to the methine that I have the red line underneath. And we also have 3 methylenes. So there's 3 methylenes. So what we'll do is we'll put the methyl down like this. And then we have 1, 2, 3 methylenes. Then we have another methine here. So we'll put this methine, and there are 2 methyl groups attached to it. So 1, 2, kind of running out of space here. But you can see that the molecule that I've drawn is B. And so B is the correct answer. Okay, question number 2 says, what is the equivalent structure for this molecule using a bond line formula? Well, the first thing I noticed about this problem is by taking a look at the double bond here, I would want to evaluate as to whether that was an E or a Z alkene. Another thing I noticed is that 2 of the answers have rings. There's a cyclopentane and a cyclohexane ring in both of these, and there's no ring indicated anywhere in this structure. So we can cross those off right away. Those are not contenders. Now going back to that double bond, if you look at the substituents, you see that on this carbon that I'm highlighting in red, the ethyl group is going to take precedence. And on this carbon that I'm highlighting in blue, all of this is going to take precedence. And so from that, we can see they're on opposite sides of the double bond. So this is an E alkene. Now, if I look at C and D, well, the first thing I notice about D is that D has a methyl group here and a methyl group here on each of the sp2 hybridized carbons of the double bond. And so it's not, this compound is not E or Z, it's neither of those. And so the answer, just based off of that, has to be C, just based off of process of elimination. And if you take a look very carefully, you can see that here we have the ethyl group, okay? Then we have the carbon in red, then we have the carbon in blue. And without me going over all the details, all of the part that is in blue, that I have in the blue box, would be all of this right here. And of course, then there's a proton, which is shown here. But anyhow, you can see that that is, as a matter of fact, this is an E alkene. So there you go. So the answer to number 2 is C. Moving on to question number 3, deals with an alcohol. You need to know your functional groups really well. And it just asks you, what is the equivalent condensed structural formula for this molecule? First thing I would do is count the number of carbons, and if you count 1, 2, remember we want to give the functional group the lowest possible number, 3, 4, 5, 6, 7, 8, 9, and then we have 10 and 11. So there's a total of 11 carbons in this compound. Now I've gone ahead and tallied them up. In A, there's only 10 carbons, and in B, there's only 10 carbons. So based off of that, we can cross both of those out. Then in D, there's 12 carbons. There's 1 too many, so we can cross that one off. But C does have 11 carbons, and the connectivity is correct, meaning everything is attached in the correct way. For example, you can see this methine here is this one here, and then you can move on from there. Anyhow, so that's how I solved question number 3. Moving on to question number 4, what's the equivalent bond line formula that's equivalent to this condensed formula here? So you can see that we've got a quaternary carbon here. That means it's attached to 4 different carbons. Now, if I draw this carbon, okay, if I put that in red like this, you can see you've got 1, 2, 3 methyl groups coming off of it. Then we have 4 we have 4 methylenes. So we have 1, 2, 3, 4. And then we have a CH3 coming off of it like that. Now I've added that letter C for the carbon in there, which is improper. It's an improper way to draw a structure, but it does kind of help you flesh out the idea. And you can see based off of that the compound that I've drawn is D. And just another aside is just solving this by process of elimination. I mean, a couple of other things here is there's nothing in this condensed formula that indicates a ring. So you can cross off these two, which have a cyclopentane and a cyclobutane respectively. And then another thing is that here we have 2 methyl groups attached to the last carbon, and you can see that's clearly not happening here. And so D would be the correct answer. Now, number 5, you need to know bond line or skeletal structures very well. And it says how many hydrogen atoms are bonded to carbons 1, 2, and 3 respectively in this bond line formula. Well, you notice that every carbon in here, in this structure, all carbons are sp3 hybridized, which means they all have 4 bonds. They all have 4 sigma bonds. Now, what can you see in the structure here is that this carbon is attached to 1, 2, 3 carbons. So that means it's attached to 1 hydrogen. Then if we look at carbon number 2, you can see it's attached to the bromine, this carbon, so there's 1 bond missing that's not drawn. And again, in bond line structures, the bonds, to hydrogens are not drawn. So this one's also missing 1. And then the last one here, number 3, you see it's attached to 4 carbons, so it's not missing anything. So the answer would be 1, 1, and 0, respectively. And so the answer to question number 5 would be A. All right, another alkene, number 6, it says, which structure is equivalent to this molecule? So again, I employ some of the same technique I did a few questions ago. If we look at this carbon, going by the rules of priority, bromine has a higher atomic number than carbon, so the bromine is going to take precedence over those 2 groups. And then of this carbon here, well, there's a hydrogen that's not shown, so that means that all of this, okay, this group here, which appears to be an isobutyl group, is going to take precedence over the hydrogen. And so this is a Z-alkene. So we'll put here, this is a Z-alkene. And so if we take a look at the answers, if you take a look at A, C, and D, those are actually all Z-alkenes. This is a Z-alkene, this is a Z, and this is a Z. But if you look at B, this is an E-alkene. You see the bromine and then all of this. So this is an E-alkene. So we can cancel out that one right there. So then the next thing I would do is I would kind of look to see, okay, well, which carbon is the bromine attached to? So if you look at this, and if you start here, you have 1, 2, 3, 4, 5 carbons. So the bromine should be attached to the 5th carbon. And so if we number starting from the far right here, I'll just use my blue pen. We have 1, 2, 3, 4, 5. So that looks reasonable. Here we have 1, 2, 3, 4, 5, 6. So we can cross that one off. And then in D, we have 1, 2, 3, 4. So we can cross this one off as well. So that kind of reveals to us that the answer must be A. And in fact, if you look at the rest of it, you can see your sort of isobutyl moiety hanging off here on the left-hand side. So that would be the correct answer would be A for that one. Okay, moving on to number 7. Which structure is equivalent to this molecule? And to keep in mind, this is a Haworth projection. It's a way of representing molecules in 3-dimensional space. And if we think about redrawing the cyclopentane like this, if I think about this carbon being up here, we can see that the bromine is coming up. Okay, so I'll put that on a wedge. Then the methyl to the left of it is coming up like this. And then if we skip this carbon, then you go 1 carbon away, this methyl group is going down like that. And so you see that what we've drawn here is D. So again, Haworth projections, make sure you take some time to understand what a Haworth projection is. Okay, let's get into electron configuration here. It says, which diagram, this is question 8, which diagram depicts the atomic orbital diagram for the valence electrons for carbon after hybridization in methane? Well, you should know what methane is. It's the simplest organic molecule in the universe. And the carbon in methane has 4 single bonds or 4 sigma bonds. And so when we start it with carbon, if we think about its valence electrons, which are 2s2, so 2s2 and 2p1, 2. Well, once you hybridize, you make 4 degenerate, 1, 2, 3, 4 sp2 hybrid, sp3 hybrid orbitals, and then you have 1, 2, 3, 4 unpaired electrons in each one. And so that explains why carbon can adopt a tetrahedral geometry and has 4 single bonds when it's sp3 hybridized. Anyhow, so that would be B. Question number 9, which of these 4 molecular orbitals filled with 4 electrons is in a ground state configuration? So ground state configuration, you got to remember that everything in a ground state configuration is going to be in its lowest energy. So if it's ground state, it's going to be lowest energy. So that means you're going to have electrons paired up in the lowest energy orbitals. They're going to obey the Aufbau principle. So you're going to start in the lowest energy orbitals. Then they're going to follow Hund's rule. You have the maximum number of unpaired electrons, but you can see that every orbital in here can hold a maximum of 2 electrons. And then the Pauli exclusion principle tells us that if you compare C and D, you might be tricked by D, but you can see that in D, everything is pointing up, okay? And that disobeys the Pauli exclusion principle, which means the 2 electrons that exist in the same orbital have to have opposite spins. So here is one is up and one is down. And then you see the same thing here. And of course, everything in C is in the ground state. The problem with A and B is that you have unpaired electrons, and then you have another unpaired electron above it. So that means this is some kind of excited state, and I'm not even sure what the heck is going on in A. Anyhow, so the answer to 9 is C. Moving on to number 10, which diagram depicts the atomic diagram for the valence electrons of ground state oxygen atom before hybridization? So this is really just a general chemistry 1 question. If you think of oxygen, its electron configuration is 1s2, 2s2, 2p4. And of course, they're talking about the valence electrons. So these are the ones with the highest N. So we have 2s2, and then for the 2p, let me just move this down a bit. Okay, if I put this down here like this, so then we have 3 degenerate 2p orbitals. Let's see if I can squeeze them in here. 1, 2, 3, 2p. And then we have 1, 2, 3, 4. So the one that would obey this would be A. All right. So A is what we have here. Again, this would be the 2s, and this would be the 2p. And this, of course, is the electron configuration of oxygen. Okay, number 11. Identify the hybridization states of the indicated atoms. So number 1 and 2 are carbon atoms. And I guess the first thing you need to know is something that we've covered already, is that if carbon has 4 single bonds, it's sp3 hybridized. When it has a double bond and 2 singles, it's sp2 hybridized. And then, of course, if it has a triple and a single, it's sp hybridized. Nitrogen, we'll cover that one in a second. So based off of that, you can see that carbon number 1 is sp2 hybridized, and carbon number 2 is sp3 hybridized. So we got sp2, sp3. So we can cross this one off. sp2, sp3. So we can cross this one off. So now it's a battle between C and D. And so we need to decide whether the hybridization of the nitrogen 3 is this one sp2 or sp3. Well, remember, this lone pair is localized. It is not participating in resonance in any way at all, and there's no double bond on the nitrogen. Therefore, it must be sp3 hybridized, and so the answer must be D. Question number 12. In a similar vein to that one is 11, so I'll leave that up here. It just says, what are the hybridization states? Carbon number 1 has a double and 2 single bonds, so it's sp2. Carbon number 2, a double and 2 singles, it's sp2. And then this one here has a triple and a single, and this is sp. So sp2, sp2, and sp. And so the answer for that one would be C. Question number 13, still sticking with hybridization. What hybrid orbitals are used to form the sigma bond between the indicated carbon atoms? So if we take a look here, we can see that this carbon is sp3 hybridized, and this one is sp2 hybridized. So sp2 and sp3 is what we're looking for, and so the answer is going to be C. Number 14, what hybrid orbitals are used to form the sigma bond between carbon 1 and carbon 2 respectively? Well, if we take a look, we can see that carbon 1 is sp2 hybridized. It's got a double and two singles. And number 2, it's got a triple and a single. It's sp, so sp2 and sp. And so the answer to that one would be D. All right, moving right along. Question number 15, still sticking with hybridization. What are the hybridizations of the indicated atoms? Let's try it again. If you look at number 1, the carbon has 4 single bonds. Of course, there's one that's not shown, right? This bond to this hydrogen. But again, this is a bond line formula. So this is sp3. This one here has 2 singles and a double, so it is sp2. And this one here has 2 singles, right? There's one single bond that's not shown, one to a hydrogen. But again, this is bond line structure, so 2 singles and 1 double. And so this is sp2, so sp3, sp2, sp2. So the answer must be D. A double bond. The double bond in 2-butene consists of what? 1 sigma bond, 1 pi bond, 2 sigma bonds, 1 sigma, and 1 pi. Well, if we draw 2-butene, so 2-butene looks something like that. It doesn't specify as to whether it's cis-2-butene or trans-2-butene, and that's neither here nor there. What you need to remember is that the first bond between any 2 atoms is always a sigma bond. Anytime you have one bond between 2 atoms, it is a sigma bond, but anything after that is a pi bond. So we have 2 bonds, so that means there's 1 sigma and 1 pi bond, and so the answer must be D. Moving right along, number 17, what are the valence shell electron pair repulsion shapes or molecular geometries associated with the indicated atoms? Well, if we look at atom number 1, there is a carbon here. Now this is a bond line structure. There are 3 hydrogens attached here that aren't shown, and there's a bond to this carbon in red. So that means this carbon has 4 single bonds, which means it's sp3 hybridized, which means it's tetrahedral. Tetrahedral, okay? If we look at carbon number 2, it's got a single bond and a triple bond, which means it's sp hybridized, and it is linear. And then the nitrogen, number 3, the lone pair is localized, so therefore the nitrogen is sp3 hybridized. Remember, the lone pair is not participating in resonance. So you've got 3 single bonds, 1 lone pair. That would mean it's trigonal pyramidal. Pyramidal. Anyhow, I can't really squeeze that in there. But anyhow, that's going to be C. So make sure you're aware of your molecular geometries. Here we go. Pyramidal. Anyhow, all right. Number 18, what is the valence shell electron pair repulsion geometry for atoms 1 and 2? Well, the first one is a carbocation. So this is a carbocation. And one thing that you should have learned in Organic Chemistry 1 is that when you have a carbocation, that the carbon is sp2 hybridized and that its molecular geometry is trigonal planar. Trigonal planar. Okay, and that has a consequence in some types of SN1 reactions, for example. If we look at number 2, is a nitrogen which has a lone pair on it. The lone pair is localized. It's not participating in resonance. So for the same reason in the previous question, this is trigonal pyramidal. Anyhow, just abbreviate there. And so the answer to that one would be trigonal planar and trigonal pyramidal. And so the answer is going to be D. Let's see here. Which of these molecules have 1 or more atoms with a trigonal planar geometry? Well, I could spend a lot of time on this problem, but I won't. If we look at BH3, this compound is called borane. And remember that boron is trivalent. It only forms 3 bonds. And so this is trigonal planar. Okay, definitely trigonal planar, the boron. So the answer has to include 1, so we can scratch D out. Then if we look at number 2, you've got 2 sp2 hybridized carbons. This is sp2 and this is sp2. So that would also mean that these 2 are trigonal planar. So the answer has to include number 2. So we can scratch out C. Then if we look at 3, there are no atoms in 3 that are trigonal planar. The nitrogen here, this is going to be trigonal pyramidal for the same reasons that we spoke about earlier. And then, of course, we have an sp2 hybridized carbon here. And so that's going to be trigonal planar. And so the answer is going to be 1, 2, and 4. And so our answer will be B. Number 20 is another question that we could spend quite a bit of time on. It just says, which molecules have net dipole moments? Well, the first, you've got BF3, so you've got boron trifluoride, you've got ethanol, and carbon tetrachloride. Well, just quickly sketching boron trifluoride. Remember I told you that boron is trivalent. Fluorine is the most electronegative element in the periodic table. There's no debating that. However, even though we have polar bonds in boron trifluoride, since it's trigonal planar, the dipoles, they're all going to cancel out, right? They're pulling in equal and opposite amounts. And so there's no dipole in this compound. So we can cross off this one and this one. Then as far as ethanol is concerned, if we draw a partially condensed structure of ethanol, you should know that the oxygen has a bent molecular geometry. And so there is a dipole associated with it like this, right? Because you tally up this dipole and you get the resultant. And so ethanol definitely has a dipole moment. And then finally, CCl4, which is carbon tetrachloride, well, that certainly doesn't have a dipole moment. It's because, yes, there are polar bonds, or slightly polar bonds, I should say, in CCl4. But since it's perfectly symmetrical, anything in there would cancel out any kind of dipole moment. And so the answer is going to be ethanol, this one here. This is the only compound here that's going to have any kind of dipole moment. Everything else, the dipole moments would cancel. Question number 21, rank these molecules on the relative intensity of their dipole moments, going from weakest to strongest. Okay, well, first of all, what are the compounds? We've got chloroform, methylene chloride, so chloroform, methylene chloride, water, and ethanol. Well, obviously, water and ethanol are going to have stronger dipole moments because they have oxygen, hydrogen bonds, right, which have a really strong dipole in them. And so those are going to be at the top, and water is going to have a stronger dipole than ethanol. Why? Because you've got the dipole moment between hydrogen, which has an electronegativity of 2.1, and oxygen, which is 3.5. Whereas in ethanol, one of them is between hydrogen and oxygen, but the other one is between carbon and oxygen, and carbon has an electronegativity of 2.5, so it's not going to be as strong a dipole overall. And so the last two have to be water and ethanol, so it has to be like this or this one. You can see we can cancel this one out and cancel this one out. So now it's between chloroform and dichloromethane. Well, if you look at those molecules, if you look at, and I don't really have a lot of space here, but if you look at chloroform, you have, all these bonds to chlorine like this, whereas if you have methylene chloride or dichloromethane, they both mean the exact same thing, then you have 2 bonds to chlorine. And so since the chloroform has 3 chlorines, it's going to have a stronger dipole than the dichloromethane, which only has 2 chlorines pulling in that direction. So that would give us D as our answer. So we'll highlight D for that one. Not a huge fan of that question, but it still stands. Which figure depicts the structure and the net dipole moment for nitrogen trifluoride? Well, first of all, nitrogen trifluoride is trigonal pyramidal. So we can cross these two off. Let me get my red pen. We can cross these two off right away because those kind of look like they're trigonal planar to me, the way they're drawn. Not the best drawing. And either way, the dipole moment wouldn't be lateral like this now, would it? So this structure is drawn correctly and this structure is drawn correctly. So the question is, does the dipole moment go up or down like this? Well, you should remember that fluorine is the most electronegative element in the whole periodic table. So you're going to have a dipole moment going this way, one going this way, and one going this way. Well, if you tally them all up, you get the resultant, which is going to be going in the downward direction as is shown here. So the answer to 22 is going to be B. Number 23 asks us which two are a pair of resonance structures. The first two in A certainly aren't resonance forms of each other. This is actually a rearrangement, which isn't even covered in Organic Chemistry 1. You can draw a rearrangement like this, and I'm not going to get into the details of that right now, but this is certainly not resonance forms. And then also in C, if you just flip this molecule around, right, if you draw a line like this, if you were to rotate this 180 degrees, you can see that those two are identical to each other. Then in B, this is a ketone, and this is the corresponding enol, and those are not resonance forms. These are tautomers of each other. So tautomers of each other, and so they're not resonance structures. But with this one here, you can clearly see in D that you could draw a resonance form like this. So you can see that these are, as a matter of fact, resonance structures like that. Anyhow, so you need to know your resonance structures for sure. And so D would be the answer to that one. Question 24 is another question you could spend a lot of time on. And if you have a question about it, don't hesitate to leave a question for me in the comments. But you might need to solve this question on scratch paper. However, it is not necessary. It's actually not necessary to do that. There are some shortcuts you can take with this one, okay? So if we put in the lone pair here on this carbon, right, we can start by pushing arrows like this, okay, where we could see that we would get the negative charge on carbon number 6. So if I just redraw that one resonance form, I don't want to take up too much time on this question, but what you'd end up with is something that looks like this. Okay, so now you've got the negative charge here, and of course you can see that you could push that out here, so it could be on carbon number 8, or you could push it out here so it would be on carbon number 4. So now we've got 6, 8, 4, and if it's on carbon number 4, it can also go to carbon number 2. So I'll leave that up to you to draw that one, but those are the 4 atoms or the 4 carbons that can take that negative charge where it can be delocalized, and so the answer would be B for that one. Okay. Anyhow, again, might be good to do that one on scratch paper. You can kind of do a shorthand version like I just did here, but if you need to get the scratch paper out, it's not a bad idea for that one. Question 25 is another one where you kind of have to be on your toes to answer this question, but let's take a look at it. It says, which is not a resonance contributor for this molecule? Well, first of all, the thing you notice here is that this is a molecule that has no charge. There's no cation or anion shown in here, so no charge. So that means that if we draw a resonance form, and if there's a negative charge, there has to be a positive charge to balance it out. Now, if you look at all 3 of these answers, B, C, and D, they all have one positive and one negative, so they all have a 0 charge. I'll just write no charge, okay? But if you look at A, you can see this cannot be a resonance form because it has a +1 charge. It's impossible to just produce charges out of thin air, so you can't go from 0 to +1, okay? So that's definitely not a charge. And also, there's no way you could draw a curved arrow to make this positive charge here. It's impossible. Can you draw a resonance form when you have a double bond between atoms of differing electronegativity? Yes, you can. However, you'd have to have one positive charge and one negative charge. So that's kind of how I solved that one, was a little bit by process of elimination. But again, you could get the scratch paper out and try to draw all of these resonance forms if you wanted to. Like, for example, let's say you wanted to draw D, okay? You would just start pushing the electrons. You'd say, I'll put a pair of electrons here, make this double bond, and then put the negative charge up on the nitrogen, and then have the positive charge on the oxygen. Again, you could draw all of those contributors, B, C, and D, but not necessary really. Question number 26 deals with evaluating the relevance of different resonance forms. It says, which resonance structure contributes the most to the overall structure of this molecule? So we have this molecule here, and we have some different resonance forms. And if we just take a look at these quickly, if we look at A, the problem with A is that the carbon doesn't have a complete octet. So there's nothing wrong with the resonance form, but the carbon does not have a complete octet. Then if we look at B, again, the carbon doesn't have a complete octet. And then we also have the negative charge on the nitrogen, but oxygen, remember, is a more electronegative element. Oxygen has an electronegativity of 3.5 and nitrogen is only 3. And so it's probably not going to be the most pertinent resonance structure here. If you look at C, what's good about C is that the carbon has a complete octet, okay? It has a full octet, and then you have the negative charge on the more electronegative element. And so if you look at D, again, the carbon does have a complete octet. Everybody's got a complete octet, but you've got the positive charge on the more electronegative element. And so if you look at all four of these, the one that's going to contribute most to the resonance hybrid would be C. Number 27 deals with carbocations. Rank these carbocations based on their stability, from least stable to most stable. Well, there's one of these carbocations that should hurt your eyes, and that is the vinylic carbocation. So vinylic carbocation, I'll just put C plus like that. Those are highly, highly, highly unstable. So the answer has to have 3 as the least stable. So that means it's going to be a battle between A and C. We can cross off B and we can cross off D. Now, if we look at number 1, you can see that number 1 has a resonance form that you could draw like this. Maybe not my best curved arrow, but you would have a resonance form like this, where you would have the double bond here, and then you'd have the positive charge over here. Nothing wrong with that. Number 2 is just a plain old primary carbocation, is not participating in resonance. And then in 4, we have a resonance form that we could draw for this one as well. And I left out my resonance arrow before, but anyhow. So we could draw a resonance form for this one too, which would look like this. But this one gives you a primary vinylic carbocation, whereas this one gives you a tertiary vinylic carbocation. And so based off of that, I would say that number 2 is going to be the second least stable, but you can see you can't decide that off of this. But again, if you look at the resonance forms that you get from 1 and 2, this one here, if I repeat myself, this is tertiary allylic, and this one here is primary allylic. Well, tertiary wins out over primary, and so the answer is going to be C, would be the best order, from 3 to 2, 4, and then finally to 1. Number 28 deals with radicals. It's a very radical question. What is the most stable radical? Well, if we take a look at these, you can see that the first one is primary allylic. And of course, if it's allylic, we could draw a resonance form. I won't spend the time drawing all the different resonance forms here, but it's primary allylic. If we go to B, this one is just a plain old secondary carbon radical. This one here is secondary allylic, and again, you could practice drawing the curved arrows for this, the fishhook arrows, if you wanted to. Maybe not my best work, but anyhow, there you go. You could practice drawing those. And then finally, the last one here is just a plain old secondary as well. And so since A and C both have resonance forms, you can see that C would be the more stable because it's secondary allylic versus primary allylic. And so the answer is going to be C. Also, when you draw the resonance form of C, you end up with something as tertiary allylic, which is kind of interesting. Next one, 29. Which carbocation is most stable? The first one is just a plain old primary. This one is benzylic. So you can draw a lot of resonance forms, or 4 total resonance forms. Also, it's secondary benzylic. This one is vinylic. That one should just hurt your eyes. It's very unstable. And this one here is primary benzylic. So the battle is between the 2 benzylics, but secondary benzylic is going to win out over primary benzylic. So the answer is going to be secondary. Something else you could do is practice drawing all these resonance forms. Just for the sake of this video, I'm not going to draw them all, but you could start by drawing this and practice drawing all the resonance forms on scratch paper. Number 30, what is a resonance contributor for this structure that's shown here? Well, first of all, if you just glance at first of all, I guess you've got this benzylic carbocation here. There's nothing wrong with that, but if you look at the answers, I think the first thing that I notice is, why is this ring in here? Okay, there's no resonance form that's going to produce a ring here. And then also, I would say, for the other ones, this one here, I mean, you're starting it with something that's positive. Overall, this is a +1 charge. This one is neutral, so that's not an answer. This one's +1, so it's in the running. This one's +1, so it's in the running right now. And this one is -1, so this one is a big no-no as well. Now, another thing that I'd ask myself is, how did you make this, how did you add a proton here? This oxygen is kind of strange. But anyhow, you can see that you can draw the resonance form to make compound C. So if we just push our electrons like this, we end up with C as our resonance form. And I hope you found this video helpful. Again, this is the ACS Organic Chemistry Study Guide 2nd edition, and this is the first chapter, which deals with structure, shape, and stability.